And welcome back. Today I have a treat for you, using the Deckel milling machine as a lathe. I have some spherical parts to machine and I do not have a ball turning tool for the lathe yet. So I figured I'm going to use the milling machine in combination with the indexing head and a boring head to do spherical turning. I did show spherical turning, spherical machining with boring head on a milling machine years ago, but that was different. That was basically fly cutting a sphere. But this time we're actually doing the same cutting process as on a lathe. So let's have a look at what's going on. So for this to work, I pulled off the vertical head, so we're using the horizontal spindle. It's just more convenient. You can do it with a vertical spindle too. And as usual, I have the indexing head mounted, but I put the wool hop, the boring head, in the indexer. And when you look at this, well, that's already a ball turning tool. You can adjust your size by moving the slide of the boring head, and you get your circular motion by spinning the indexing head. That's all a ball turner is. You're moving a single point tool on a circular path. All I had to make was this little tool holder bit that I will show you in a second. Work holding in my case will be done with a hydraulic chuck because that's it's a very stiff way of holding things. I made some arbors for the parts I have to make. Well, here's one of the parts. This is a scrap one. 19mm sphere machined on the inside to go on this arbor. And the arbors all have a 12mm shank that goes in the hydraulic chuck. Also, the hydraulic chuck builds up a little bit of distance so I don't have to extend the y-axis out as far, or since it's a horizontal mill, the z-axis out as far. Here is the tool. This is a piece of 18mm precision ground stock, case hardened linear rod. I just use it because I had it on hand and it has a nice precise diameter that fits the boring head. And I milled an insert pocket in the end of it. So it fits a DCMT-07 carbide insert. And the insert just sits there in a pocket. I didn't even bother to mill the 7-degree clearance of the insert into the pocket. The pocket just makes line contact with the insert. That's fine for this purpose. It's not a high performance roughing tool. And that's all we need. And the tool can be swung like this. It has a large flat machine on the side here to allow me to adjust the clearance against the shank of the ball that I'm turning. We're now looking straight down onto the carbide insert. This is the damaged spheres that I'm using as a demo piece. And as you can see, there is not much clearance on this between the tool, carbide insert, and the shank here. I already had to do a little bit of trickery by spinning it. If you look down at this boring head, the center axis of the boring head goes more or less like this. Well, more like this. And the tip of the insert is spun to the side to allow me to clear everything as I need it. I don't want to make this 5mm shank here any longer than necessary to reduce unwanted vibrations and give me as much stiffness as possible. Spinning the insert off center line doesn't affect the creation of the sphere because the tool tip is still rotating on an arc. The tool does not have to be perfectly neutral. It doesn't have to be like this. It doesn't have to be. You can do what I did here and be perfectly fine. And by doing this, you get a little bit more clearance back here. This is also always a little bit of a problem with ball turners on lathes. They often are not designed to give a decent clearance in this area when you want to make a sphere with a shank, like if you want to make a ball handle for an old school machine tool. So this is the actual sphere turning process. The spindle of the indexing head is directly in line with the spindle of the milling machine. So we are creating an actual sphere and not some weird oblong shape. Depth of cut is a little bit limited because the arbor this blank is mounted on has only a 5mm thin shank where it reduces down to the ball shape. So I'm taking fairly light cuts, going back and forth, just feeding in very slowly on the boring head. And this way you will slowly generate a full sphere, or as much sphere as you can create with a shank. So in this setup you can see the orientation of the carbide insert in relationship to the boring head, and this allows me to cut into the corner between the sphere and the mounting arbor. So these parts are for Centenario, who build unique wall clocks, and since they are aesthetic parts, the finish has to be rather nice, and also they will get metal plated, and with metal plating all surface finish from the actual part will show up through the metal plating. So I'm hitting them with some gray Scotch-Brite and follow up with 15 micron aluminum oxide polishing compound on a paper towel. And I follow up with some 5 micron aluminum oxide polishing compound. Using a piece of 1mm polyurethane rubber to give me some grip when unscrewing this sphere. Here I'm machining a semi-sphere part out of delrin. You get an impression how I operate the indexing head and the boring head at the same time. My left hand adjusts the diameter of the boring head. That's the nice thing about the wool hop, the boring head. You don't need a wrench to adjust their size. They have a large knurled ring that you just spin, and there is also a very good graduation on it, so you can read what you adjusted. This being delrin, it's of course very annoying with the chips because we cannot feed hard enough to break the chips. As usual, this was not my idea. I found this concept in the Deckel Technical Bulletins from 1974, and this was a chapter about precision boring. But boring being a turning process, they added a short section about OD turning too. And here is this very setup with the horizontal spindle, boring head, and a turning tool to do ball turning. And an additional option down here with the vertical head, they sold a 40 taper 3-jaw chuck, by the way, that fits the spindle. And with the head tilted, you could do a sphere with a tapered shank. So you would do the sphere with the with the rotary axis, with the indexing head by spinning it. And then you do the tapered section by lowering the z-axis of the mill. That would do the taper turning. Also notice that the indexing head is hanging off the back of the table quite a bit here. It's holding on with 2 screws here. So that's where I got the idea for using this machine as a ball or sphere turning machine. So this chapter about ID boring was quite neat. It showed I think this is Deckel FP33 with a Woolhopper UPA4. That's a very standard operation. Dude is holding the torque arm to do a facing cut. The boring head feeds out on its own when you use this. This down here is a Deckel FP2LB. That's the traveling column machine. The table is stationary and the column moves along the table. But what's quite neat here, let's zoom in. They have the right angle head and holding a UPA1 boring head in here. And they are boring along the x-axis a half-round groove or a channel. That's quite a nifty setup here. They go into detail with boring tools, tool angles. Over here we have a Deckel FP1 with the specialized boring head. This is like the vertical spindle, but it runs in angular contact bearings, so it doesn't have the tendency of the normal milling head to create slightly out of round holes. This creates truly round holes. Has a longer quill travel of 100 millimeters. It has a quill auto feed, but you need the riser block. You cannot put this directly on the y-axis. And down here, this is I think this is a FP4 doing some horizontal spindle boring on this casting. Some metrology, ID mic, and down here, that's interesting. That's a tool for setting the tool bit on a boring bar. You know, if you have a boring bar that has just the tool clamped with a set screw, there is this tool that you can rest on the boring bar and has an indicator to measure the tool stick out. Let's talk about ball turners or radius turners in general. I have been thinking a lot about them. The logical answer would be to do either a CNC conversion of this machine or to get a small CNC lathe. But being who I am, I have a mental condition that doesn't allow me to do a CNC conversion of this machine, nor an electronic lead screw that can also do radius turning. This machine will stay manual. And currently, I don't have really much space for a CNC lathe. And also, I kind of enjoy the mechanical aspect of a ball turner. So there are a number of designs with ball turners that are more or less practical. You see, this is just a mock-up. This is my small Woolhopper boring head in a more steeper sleeve. But you see this arrangement a lot for ball turners, usually with a little bit of a bearing arrangement in here or with a plain bearing, with a lever on the back side to have some leverage when turning this entire boring head. And often people even use a boring head for this kind of ball turner. Boring head in some kind of a sleeve with bearings and a tool sticking out the front. And this allows you to do convex and concave spheres and partial spheres, but usually the center of the sphere is on center with the lathe spindle, so you cannot do corner rounding, for example, or cove cutting. I will show you that on the bench in a second. this is really mostly for doing spheres, and it's great. It's great for that purpose, but it cannot do much more. Basically going through this motion to do your turning here. One of the problems, apart from being locked on center line, basically, is the closer you get to the chuck, the trickier it gets with clearances. Also, you can run out of cross-slide travel. I'm already backed up all the way, and this arrangement with the Wohlhaupte would not really work with that long of a tool. You need a little bit of tool stick out depending on the size of sphere you want to turn. But that's all a solvable problem if you go with this arrangement. Bilz made this style of ball turner, but with an additional dovetail slide. So the additional dovetail slide allowed you to have it up here. That allows you to do either like corner radiusing or to do cove cutting. So I'm adding in the paperwork for the Bilz ball and spherical turner, and here's the device. They made several different sizes, and the larger ones, well, are a two-man job to lift on a machine, but the smaller ones can be dealt with a single person. And as you can see here, in this first picture, they have the slide in front here that allows you to adjust the radius. And the second slide, a little bit back, this allows you to adjust the position of the radius. So you can do, for example, on this hand wheel, this radius. And they have a worm drive to spin your cutter back and forth, which gives you, for one, mechanical advantage and a more even feed when you hand feed. Here is the setup with the hand wheel cutting an offset radius, and over here on the left side we're cutting a sphere with the spherical center on rotation center. Here are the size 1, 2, 3, and 4. Size 1, the smallest one, can do an 80 millimeter sphere and weighs 20 kilograms. Size 4 can do a 500 millimeter sphere, but weighs 52 kilograms. They also made these concave turning devices, which are quite neat. They have this little rotating head with a tool adjustment screw back here for the radius, and a worm drive that goes in from behind, well, from the side at an angle, so you can also work inside of larger bores, or you can do things like rope pulleys. These also came in 4 sizes, and again, the biggest one with 33 kilograms is quite the thing. Let's see what else we have. Yeah, there is the size, the U0, which is the smallest one. This fits almost on my Weiler lathe, I think. But those are not meant to go in the quick change tool post. You have to remove the tool post to use these properly. As you can see here, they pull off the tool post and bolt it directly to the compound slide. Ball turners, they are rare, and when they show up, they are rather expensive, and they are heavy. They are really fairly large and heavy devices. Would I like to have one? Yeah, I wouldn't mind one, but am I really looking actively for one? Nope, not really. So that's one option. The other option, I have to do a little bit of improvising here, since I don't have a ball turner like that, nor the parts to set it up, so We're doing some paper cutouts here. This would be the spherical turning attachment with a vertical rotary axis. And you could set it up, for example, to do concave cutouts in the face of a part, just like this. So you would start basically out here, rotate back and forth, and after each partial pass, you would feed in a little bit, go in and go back and forth, and whittle your way until you are at your desired depth. Measuring a spherical pocket is another problem then. You can also do like spherical pattern or spherical grooves on the side of a part, like this. That's a case where you will run out of x-axis travel very, very quickly. It might be reasonable to have your tool on the back side here, like this, and run the lathe in reverse. And cut it on the back side. Otherwise, x-axis travel might be a problem. Then you have the option to have a tool holder like this that has the tooltip facing inwards, and this allows you to cut, for example, corner radii, like so. Just rotating around the center point of this radius, cutting the edge corner. Of course, it can also do spheres or almost full spheres. You always need something to hold on to, like this. And spheres, and of course, if you can do a sphere, you can do a semi-sphere too. You can do this and cut just a half sphere on the end of a part. So this variant can do a lot, and you're using already the travels of the machine. Two things to consider. It's a little bit more setup time to bolt it down on the back side of the cross slide here, compared to just dropping a tool, a radius or ball turner into the quick change tool post. You have to bolt it down somehow. You have to find the center of rotation of your ball turner and go from there. But once it's mounted, and you calibrate it in the DRO, you're good until you remove it. And I can already hear you screaming on your computers. And Inherent Machining made these very publicly known, but they existed for a very, very long time. This is the double eccentric ball turner. There was a German company who made these. They make Schnitzelpressen now. You can look them up on the internet. This is the original website of the designer of the double eccentric ball turning tool or radius turning tool, Endescon. They build special machines, do custom machining, build a Schnitzelpresse, and also this radius or spherical turning attachment. I'm not sure if they still build it because the website for the radius turner is dead, orcosys.de. But we can take this and put it into archive.org, the Wayback Machine, and check older snapshots of the website. So here is a very old website from 2004, already showing this radius turning tool, even animated. That's quite neat. So here we can see the entire operation of the tool, basically. That's quite neat for the time. Let's see. I love old websites like this. But up here you can see the tool. He made several sizes, like 5 of them. And the R, the number always dictates the maximum radius of the tool. These are the sizes. Yeah, here's a picture of them compared to each other. I was hoping for some pictures of it in use, but I cannot find them. Let's try a slightly newer website. There used to be a great video on using this ball turner. Somebody uploaded it to YouTube. You will find it. Oh, it even loads. I will not show this entirely because this might get copyright striked. But you will find this on the internet. It's a great video. It's very, very 2000s. And it's in potato quality. That's what we had back then. It's two eccentrics that are coupled via a worm drive. It's basically two worm gears driven with a combined worm screw. And those two eccentrics move always synchronous. So the idea is if you mount the tool on here, on those two eccentric points, and you crank both eccentrics simultaneous, the tool goes on a circular travel like this. And this allows you to do, this gives you all the options. You can do everything. You can do, so for example, you can do a full sphere, partial full sphere. That doesn't make sense. You always need something to hold on. So it travels around the sphere. Of course, you need a tool holder or a tool that will not intersect with the part depending on your tool motion. But as you can see, this is perfectly fine to do a sphere. If you want a little bit more clearance, you might use something like this, a hook tool with a button style insert. So outside, it can do corner radiusing. It can do, let's quickly, man, if all parts were that easy to change over, like these paper cutouts. You can do cove cutting like this. I think that's a woodworker term. So you can have it travel through the cove like this. It can do the facial groove like this. You get into clearance problem on the back side here with this tool holder, but you get the idea. And what none of the other radius turning tools or ball turners can do is this. This thing can come in. Yeah, ignore that we're crashing into the part here. But what it can do is it can do a radius on the inside a bore. Since the circular motion of the two cranks telegraphs directly to the tooltip, it doesn't matter where you're cutting. If you're out here, it's doing the same motion still. That means that you can perfectly fine reach into a bore and cut a radius on the floor of a bore. Looks like a nightmare to do in practice, but it's possible. And what you can also do is you can come back here, change your tool, and you start here somehow, and you crank like this, and you can do a radius ID groove, fairly large radius ID groove, because you need clearance for the tool, but it's a possibility. This design with the two eccentrics and the worm screw is really, really nice. It's a very, very clever solution. It's mechanically not trivial. Endurance machining already noticed that there are some pitfalls. I think the double worm gear is the reasonable solution. The crank, he tried it with a parallel bar, and there are positions where it wants to lock up and you get into weird backlash issues, and it's just not a huge fun thing to deal with. So this double eccentric design might be interesting. Here are all the parts I had to make for this order. Full sphere in aluminium, brass, and 14305 stainless. Half sphere in aluminium and brass, and half sphere in black delrin with some features cut on the inside. The overall machining and tolerances on these parts are nothing exciting, but making spherical parts is always kind of neat, and using the milling machine for this task was quite enjoyable. It's a rather rigid setup. The mill spindle the horizontal spindle of the decal is very rigid, to be honest. So work holding is always tricky with spheres. In this case, the customer had planned to put them on an arbor for machining. So I have a M4 thread down in there, and the arbor has an M4 thread and a precision diameter here that centers the part on this counterbore. So that's nice. That's a fairly decent solution. But still, the interface here with its 5mm diameter is on the edge of possibility. I don't think this would work with a 4mm stem anymore. This would be welcome to Cheddartown then. The stainless steel sphere was already tricky to cut. I had to reduce the depth of cut quite a bit to be able to achieve a chatter-free finish. But, well, got it done. And clearance is always an issue with ball turning. A lot of the ball turners that you see for lathes are really, really bad in regards of clearance between when you go past the first quarter of the sphere. Well, once you go over the equator. The rear side is where it gets tricky with ball turning. But this worked out quite nicely. I will continue to think about the perfect ball turning tool for the lathe, but well, I wouldn't expect anything groundbreaking. Until then, the milling machine with the indexing head and boring head will stand in as a ball turning machine. So I hope you enjoyed, hope you learned something, and well, thank you for watching, thanks for your support, and I'll be back.